When a bone snaps today, a highly coordinated system kicks into gear. Within minutes, paramedics arrive, stabilize the injury, administer potent painkillers, and rush the victim to a sterile surgical suite. 50,000 years ago, the exact same injury happens in total isolation. There is no ambulance, no morphine, and no infrastructure to catch you. Instantly, an electrical signal rockets from the torn tissue to the brain. This acute pain is an essential survival mechanism, a blaring alarm organism to immediately pull back from whatever is destroying its body. But when an injury is catastrophic, the sheer volume of that signal can trigger a paralyzing physical shock. Without modern anesthetics, our ancestors had to find a way to endure the absolute peak of agony without their bodies shutting down entirely. The second a major trauma occurs, the nervous system enters a state of panic. Heart rate spikes, blood pressure drops, and the body prepares for systemic failure. To prevent collapse, the brain initiates an immediate chemical override. It floods the bloodstream with adrenaline and endorphins. These neurotransmitters physically bind to receptors in the spinal cord, intercepting the pain signals before they can fully register in the brain. This chemical flood operates on a strict timeline. It provides exactly enough numbness to grant a hunter the strength to fight off a predator or scramble to safety before the body's natural defenses are exhausted. This biological trick guarantees an immediate escape, but it does nothing to fix the underlying damage. Once the adrenaline burns off, the victim is left with the raw, excruciating reality of the injury. The real test begins on day 1 of recovery. The internal biological painkillers fade away, and a deep, pulsing, inescapable agony sets in. Through generations of trial and error, early humans learned to scan their environments for chemical relief. They identified specific plants, roots, and leaves that contained active compounds capable of dulling physical misery. Ancient foragers discovered that chewing on the bitter, rough bark of the willow tree released a compound called salicylic acid. Today, we synthesize a nearly identical chemical in laboratories and call it aspirin. Surviving the grueling weeks following a trauma required a transition from passive brain chemistry to an active mastery of environmental chemistry. Chewing bark could not fix structural damage. For a nomadic hunter-gatherer, an unaligned bone fracture meant permanent immobility, leaving them unable to gather food or evade threats. The fractured pieces had to be manually forced back into proper alignment. This required someone else to grip the limb and physically snap the jagged ends into place, completely unmedicated. Once aligned, the limb was wrapped tightly in stiff wooden branches and animal hides. This rudimentary cast locked the joint in place, enforcing the rigid immobility required for the bone to fuse back together. To restore mobility, our ancestors chose to inflict intense, short-term suffering to prevent a lifetime of deformity. Sudden injuries were only half the battle. A slow, rotting infection inside a single tooth could spread into the jawbone and bloodstream, turning a dull ache into a lethal, systemic threat. This jawline reveals the extreme measures taken to fix such damage. Archaeologists have found prehistoric teeth showing clear signs of deliberate scraping and manual drilling into the enamel with sharp stone tools. After excavating the decay and exposing the raw nerve, early dentists packed the cavity with a thick paste of beeswax and medicinal herbs, sealing the hole to prevent further infection. This diagram illustrates a deeper biological challenge. As hominids evolved to walk upright, their pelvises narrowed while their brain sizes rapidly expanded. This created the intense mechanical friction of an infant's head passing through a restrictive bipedal funnel. Pushing through labor or surviving the crude excavation of a rotting tooth proved that internal endorphins and chewed bark were insufficient. Survival now required a coordinated, external support system. The proof that our ancestors successfully endured this gauntlet is quite literally buried in the dirt. Modern excavations give us a direct physical window into the toll they survived. Among the most revealing artifacts is a prehistoric human femur that had been snapped completely in half, yet shows the smooth, calcified growth of a bone that fully healed. It takes 6 to 8 weeks of strict immobility for a femur to fuse. In the logic of the animal kingdom, an organism that cannot walk for 2 months will succumb to starvation, dehydration, or predation in a matter of days. The presence of this healed femur in the fossil record suggests that for once, the unforgiving laws of predation and hunger were suspended by social intervention. If we reverse engineer the survival of that specific bone, we find the labor of others. For that fracture to fuse, a group had to provide food, water, and protection for months on end. Endorphins provided the initial escape, and willow bark dulled the daily throb. But persistent caregiving allowed individuals to survive injuries that would otherwise be terminal. Humanity's earliest hospitals existed as the protective, empathetic bonds of the family.